and that will be Dr. Ricardo Rodriguez, who is with the Raytheon Corporation, specifically in their Intelligence and Space Division. He is a fellow with the Raytheon and with over 23 years of experience. He was one of the contributors to the MSAD project, Capstone project, and in particular in the cybersecurity area. So, Ricky, would you like to take it away? Thank you.
Good afternoon, and thank you for the introduction. Let me see here if I got next. So over the next few minutes, I'll be going over some of the work that we did a while back as part of MSAD in terms of how do we use AADL to do some modeling of an attack, and how we were looking at really how can we use that modeling to be able to generate quantitative data that can help us truly get to the point where we could determine potential KPPs as part of the cyber resiliency effort. And basically, we'll go over the brief overview. I'm going to go somewhat in depth. I know there's plenty of slides, but because we have some notes that are somewhat similar, I don't think it will take that long. And the idea is that I will walk you through almost like a recipe on some of the steps that you could take to potentially perform similar approaches. And ultimately, right, the result of this is a somewhat of a process in the process that we used and how we applied to actual using some data that we gathered from a small form factor mini lab that we built for gathering actual live data that could be used by the AADL models. So why AADL? I think one of the key things that AADL brought to the picture when we look at this challenge, if you will, is the fact that it includes that behavior modeling. I mean, we know that sometimes, when we start doing analysis, one of the key things is how do you create that gap between having some detail and potentially even parametric things that you do, and then being able to not necessarily having to use a full-blown simulation package, right? So I think AADL is somewhere in between that kind of helps you provide some capabilities that are built in. And ultimately, we ended up leveraging the resource budget allocation and latency analysis from OSATE to do the actual analysis. It's reusable and extensible. I mean, I think for the approach that we're taking, we focus on denial of service primarily, even though we started looking at man in the middle, but we could potentially use this for any type of attack that exists. Ultimately, even the high reuse from the models that you create. And the ultimate goal, as I mentioned, is generating those KPPs. I mean, over the years, right, we hear cyber resiliency, cyber survivability, and when we talk about cyber resiliency and KPPs, and we have pillars, those key performance parameters, right, trying to get in front of that early design, the architecture and the early design, so we can have those trade-off analysis. I think this is what this approach was able to provide. In particular, when we talk about withstanding, right, you basically you want to operate under an attack. Okay, so a denial of service, for example, you can, if you understand what that denial of service look like within specific bounds, right, you'll be able then to plan a design that can actually withstand that attack and be able to still perform the desired function. And of course, with that, the goal is to, once you have those elements in front of you, and you have the other disciplines involved in the decision making, you're able to really understand better the conditions, so you can then select the proper approach to truly enhance the defense in depth approach of your system, and sometimes even not requiring any additional countermeasure. Because if you're truly designing to withstand within specific bounds, then at that point you don't really worry too much about that attack in particular. So this next chart is a notional description of what I just described. And if you look on the left side, as you have a denial of service, you may see something like this. It can vary depending on the system, the type of attack, but you may start seeing your throughput, right? Definitely start going down. The throughput measured from the end processes that are trying to communicate. And then you have your CPU utilization at some points may start going up, and of course the memory as well, depending on the attack. And the latency ultimately is one of the key issues, right, that we can experience, especially when you're dealing with real-time systems or time-critical systems, right? We design pushing the envelope in technology, trying to maximize throughput and resource utilization, and doing this optimal type of design decisions in order to, like I said, push the envelope with technology. One of the key things that we worry about all the time is latency. And in this particular case, there's we call it application timeout. If you have a distributed environment, at least 2 nodes, and there's some communication between those 2, and the algorithm that you're implementing, we know that there's certain limits as to how long you can wait to get some data from each other, right? So this is where I'm depicting here, and as you can see, once your latency hit that particular point as to maximum timeout, right? You hit that point, well, now you created a denial of service. So the goal is, by being able to simulate this and understand what it looks like on a system, then you go to number 2 and you start discussing what are those trade-offs, right? What can we do? Well, if we identify that a particular denial of service within specific bounds, especially on the type of system that we deal with, if you have a vehicle, you cannot bring, you're not going to have a supercomputer launching a denial of service, right? You may have a more portable system that will have a limit in terms of capacity and ability to do a really intensive attack. So now you can then look at that and say, well, do we have any margin on the timeout? Is it possible to push it? And in this particular case, it just happened notionally that, hey, we increase the timeout and the function of the system is not impacted. So now you can really withstand that attack. And by withstanding that attack, really, you don't really need any countermeasure. I mean, not that you won't do that, but in the end, you're designing with that type of attack in mind. So that's the ultimate goal. This one, even though I'm not, we didn't go in depth into this, and the presentation doesn't really cover much of this, but similarly, we look at man in the middle, and we said, okay, one of the well-known attacks, and there are countermeasures in place most of the time, but some systems may not have the ability from a COTS perspective or existing approaches to prevent the MAC spoofing, which we know is a real issue, right? And it's a real, there's many variations of this. And ultimately you have 2 phases. You have the passive and the active. So if you're able to do measurements and understand your system and gather live data to the point that you can really measure that latency variation, you could, in theory, right, when we look at the man in the middle impact on the left side, being able to really measure and understand potential variability on latency that could be an indicator of a potential man in the middle attack. So that's ultimately, one of the values when you start looking at how do we not only design for cyber resiliency, but what can we do from the concept of detect. This chart covers a brief description of the portable small form factor lab. We have, you can look at the specs here of this 2 units. One, we had a Kali Linux in it, and the other we have Windows 10 acting as a victim. And we have a older Cisco 3550 switch. And as you can see on the left, it's just a high-level summary or representation of the type of data that we got when we launched the denial service. We're using, from the open, the CNAC attack. So if you're familiar, those of you that are not, or you are, a 3-way handshake that happens on TCP It's a common type of attack where you're trying to generate more requests without replying to the first acknowledgement. So that way you can keep open sessions and that start consuming resources. So in reality, in this type of system, then you see what it looks like. CPU start going up at some point. So in essence, you keep opening and processing things. Memory was, there's some, depending on the attack and the variation and the type of technologies that you have, memory may not be impacted like in this case. And then of course your bandwidth ultimately will lead to some of the, will also contribute to the latency issues. So the next number of slides, I will go, this is actually what the model looks like. And as you can see, on the attacker side, we start by, defining, the processor, the RAM, the ROM, and an internal communication bus. Those of you are familiar, most of you are, I guess, are familiar with the AADL. And it's very straightforward, right? It's something that, again, you can show the value of AADL to do some basic analysis and be able to reflect some known system or systems that as you get live data, you'll be able then to do proper analysis for your design. In the case of the attacker software, of course, you're looking at the threats, and in this particular case, because it's the attacker, the threat truly represents the denial of service attack. And this is where you basically, before we had the hardware, the one before, now we're looking at the software. And the next one is really the device with internal interfaces that support the hardware and software models that we were kind of describing before. And also model it's actually required. It's a requirement to make sure that we can model latency and bandwidth between the attacker and the victim nodes that we're going to be describing in a few slides. And of course, the actual implementation. Now, this is the attacker system implementation. This is where we put all the parts together. We have the hardware, software, and the actual interface. And as you can see, right, when we talk about the capacity versus the budget, you can see it on the chart. And then, of course, you're going to have the type of connections between those components and the interfaces. So again, if you go through the process, you see it's a very straightforward kind of taking baby steps on how you put the parts together for this particular attack modeling. So similarly, when we look at go to the victim side, we're really performing the same approach. So now we have the same type of elements and components of another node. The key difference in this case is that when you get to the actual software, right now we're doing the hardware similar to the attacker, where you have the ROM, the RAM processor, and the communication bus. Then you get to the software side where the thread, even though it's kind of a similar instance, pretty much a copy and paste, almost, right? At this point, it's really representing the actual thread that is the function that the system is performing. So that's how we approach the definition of the two nodes. Okay. Same as before, basically we have the victim interface for the denial of service, and again, it's really required to model the latency and bandwidth between the victim and the attacker nodes, and of course the interconnection between the different element and the different interfaces from the different components. Okay, and similar to the attacker, then we have the system implementation, and as I touched on last time, you're basically looking at the RAM capacity, MIPS capacity on the processor, as well as the budget on the process itself, right? You have the hardware capacity and then the actual budget being allocated to the process, in this case, the victim. And then your interface, where you have the different type of connections between the interfaces so it can enable the flow, right, between the different components of the system. So now that we had the two nodes, the next element is create the denial service system. So now we're trying to, basically when we look at denial service, we already created a denial service attacker, right? And we ended up with a system implementation of it. We did the same with the victim. Then we have the Ethernet, bus here, as well as the network switch. And the idea is that you're basically that with that switch, that's a key element, right? That we know in networking, you're going to have the communication between two or potentially more nodes, and the switch will actually be used as a main third element on the system when you're trying to do the MAC spoofing. And that's primarily because the switches, even though the old approach OS, you could do something similar on the switches, that was the big deal, right? The MAC spoofing element as well. And then the denial service, because then you're able to start not only on the interface, but on the backplane. So that's how we ended up deciding, hey, let's not just limit it to the nodes direct connect, let's go through a switch. And denial service in particular is a key component of pretty much any network nowadays. So in this particular DOS system implementation, here what you see are the previous system implementations for the attacker, the victim, as well. Now we have the network switch. And what you see here, you're going to have the flows, right, which is the source and the sink. And you can tell that ultimately, right, this type of flow and having a transmit and receive bus, if you will, right, between for each one of the nodes, and then you have the flow source and the flow sink. That really is what when you put the latency element, right, it's what enable that the proper allocation of the data between capacity and budget, especially in the bandwidth, to make sure that we can really truly simulate or do analysis that can lead to representative data from a real system, or at least based on live data, in order to do a proper analysis. And as you can, the bus custom component, it's like I said, it's and the sink and the source, right? Those are some of the key elements that you really need to pay attention to when trying to do this type of interconnectivity for this latency analysis. And then we ended up adding ultimately, right, values were added to each leg of the path, including the flow path defining the victim node. So again, there's on previous presentation, when we talk about the budget versus capacity, and how when you have, for example, in the hardware, certain allocation, the way that we did it, and then you're looking at what is the budget for the thread and the elements. We use those elements, and we have the maximum and minimum as well, in order to represent the environment in such a way that when you do the OSATE built-in latency analysis, you get a pretty decent, pretty accurate results. And that concluded the denial service. I'm only showing the man in the middle, even though we didn't go in depth into it. But similarly, when we went to do the man in the middle, as you can see, it's pretty much the same. The only difference is we are adding a third node, where before we had an attacker and a victim node. In the man in the middle, what you end up doing is you have two nodes that are considered victim nodes, right? And then the attacker, which pretty much remain the same. And of course, the amount of interconnections increases, right, as you add more nodes. So the same with the switch, right? Now you need 3 ports instead of 2. But it's a similar approach. You can tell from a scalability perspective, it's an easy to follow approach. And then, of course, from a reuse perspective, significantly reusable, not only for man in the middle, but all the type of attacks. The next few slides, I'll start going a little bit more in detail into the attack and the analysis. On the left side here, you see the parameters of the actual hardware that we use to get live data. And on the right side is really the attack that we perform. And you can primarily look at the bottom. So even though we didn't do what we consider full latency analysis, I think from a variability measure and closeness, we were trying to rely on simple ICMP round trip numbers. But then from an attacker perspective, you can see we use HPing3. And really what you're doing is, I consider that a ping on steroids. You have many things you can do with it. And ultimately you target a particular IP address, right? The interface of the victim. Then you have how many packets, and of course we vary that because you want to do more and more. And then you basically do faster, which is a combination that is -I, and I think it's 10,000, where you're actually even maximizing more and more generation of the packets. And then in this case, the sync flag, this is what actually enables the attack. And then ultimately, we ended up using port 135. Typically, when we do an nmap scan, which we did at the beginning, right, part of the goal is to identify what ports you have system listening on, what type of services. We know in the case of a Windows, which we used as the victim, port 135, even though officially it's a port that is supposed to be more for remote connection, right? Or remote procedure type calls. It's also one that provides services to understand what other services exist and the logical ports on a system. And that's why when you look at the data over the years about attacks and what can you do with it and type of vulnerabilities that came out, a lot of them you can trace them back to that port 135. But we decided to use that one as the actual target for the denial of service. And over here, you're going to see on this slide, as we ran on the live system, the attack, you can see as we increase the amount of open connections, which is half open connections, as you generate those TCP type of CNAC requests, right? You're keeping things open, you are not responding. When you get some reply back, you just keep it, no handshake, no final handshake. And as you keep those going up, you're gonna see how your CPU, primarily, your RAM didn't change much, your CPU, actually nothing at all, almost, and your CPU really started going up. That's where we noticed a big difference. And then the bandwidth, of course, you're gonna see from the receive and transmit, you're gonna see some variability as well, right? Because you're generating, of course, more data on the bus, right, on the Ethernet connection. And then your latency and your baseline, as well as your measured latency. And as you can see here, when you get somewhere between 50,000, start going up more than 10 times, and it just skyrocket after that. So that we did this a few sample runs, we got enough data, so we can use that as a way to update the model and assign the different values so we can do further analysis. This next chart is the same data graphically. As you can see, we have, as I mentioned, on the victim side, the latency, somewhere between 50,000, 100,000, and then 10,000, 5,000 and 10,000, you start going radically up. So with that, the next few slides really more of a detailed show of the output and the process. So these are the the steps that we came up with, and they're straightforward, right? We have to design select a threat and an attack. You develop the AADL model that represent, and like I said before, there's a high reuse when you pick different attacks. The lab system and measurements, right? You're actually doing actual measurements of a representative system. You can perform calculations, and then you add values to this model in order to do the OSATE analysis, with the ultimate goal that now you can do some cybersecurity analysis. Now you can sit at the table, right, with some quantifiable data to start looking at, based on certain type of attacks, what are those trade-offs that we can make as engineers early on in the architecture and design phases. I'm not gonna go through all the details, it's just all the data points that we gather, following the steps that we followed. And as you can see, right, we went for the threat attack selection, AADL models, actual measurements with the calculations. And the beauty of this is, right, once you do it once, it can be highly automated, right? You have even if you do spreadsheets, and then of course gathering real data from a live system that can also be, I would say easily automated, to the point that having some live systems being able to to gather data and play what if scenarios. And as you make changes, I think it can significantly generate a better data set over time. So you don't really need much live data anymore, right? You can just extrapolate and do some educated design decisions, and how will those impact the overall latency. And then the last step here, where we actually added the budget values, capacity and budget values to the AADL models. So with that, the outcome of this particular case, as you can see, right, is CPU was over capacity 16% after the denial of service attack within the bounds that we actually specified. I show you in terms of the amount of open connections. And when you see the rest and you're looking at, well, the others resources are still under capacity, I mean, that's a very telling story, right? And like I mentioned with the automation, where you build a good data set based on real life data, and now you can quickly run an attack or simulate an attack and be able to get these type of results, really is very eye-opening, right? Now you can take this and say, based on this, what can I do as a cybersecurity expert? Well, I mean, we know the CPU margin was exceeded by 16%. And granted, you never hit the 100%. Maybe you limit yourself to 75 to make sure that you have margin. But ultimately, you know this data point. And now you have multiple decisions to make. I mean, whether you generate a new higher CPU designed with a higher CPU processor, whether you do determine the number of open connections or sessions that you're going to limit, and you can adjust the CNAC timeout value. And this one in particular, the CNAC timeout value, it was very telling the value of AADL in my mind when we went through this process a while ago, because there's well-known values out there that are published via STIGs, security technical implementation guides, and other documentation and recommendation from vendors, but nothing like knowing the real value, right? So now using AADL, you can tailor that value. And of course, you still have other type of mechanisms that can be applied as countermeasures, such as microblocks and reset cookies, stack tweaking, you name it. But again, the point early on, the goal is how can you really get quantitative data that will enable that early trade-off analysis and decision-making. So with that, I think I'm almost out of time, but thank you for your time and attention. And any questions?
There was oh, thank you for your presentation. I think you've added quite a bit to it since the last time that I saw it. We did have an earlier question from Scott Kenny that was probably addressed to you and to the other presenters about using AADL tools in other kinds of environments and a variety of types of data buses. Jerome joined us, I guess, after lunch, so he did answer it, but I don't know if you had anything that you wanted to add about this question.
I think I watched all that. It's definitely well answered. I mean, I don't think, I think the element of the environment, when you look at, I mean, maybe not directly related to the question, but I mean, I know there's many tools out there, and there's a lot of how we can integrate with this, how we integrate with that, and what type of features or benefits you get. And in the case of looking at any type of environment, as engineers, right, when it's all about quantitative data, right, and I have to say that I've seen cyber, my personal opinion, right, it's been progressing, and I think regardless of the environment, and regardless of even when you do only Ethernet, or even if you do 1553, or you have the ability to do behavior analysis, right? And I think that's really the forte of AADL, that in my mind, especially as a cybersecurity expert, right, I want to have a seat at the table early on and be able to quantitatively, not necessarily having to add tons of countermeasures that can derail the mission on the system, But if I design and I got data that is quantitative, and I can tell you what the limits are on my design and what type of attacks I'll be able to withstand, I mean, that is a cost-effective approach to dealing with some of the challenges that we have to deal in this environment, in any other environment, right? Most of the larger environments, you deal with COTS products, right? And you can throw many things at them and many functionality. But when you're looking at real-time small system that worry about SWAPC, right? The weight and everything else, I mean, you really need to use something that can help. And AADL just happened to be that tool that I think can significantly help address some of the challenges in trying to bring cyber to the embedded world.
Just one more question that had to do with modeling countermeasures within AADL. In addition to tracking the man in the middle or other attacks, we do any countermeasures, if we model any countermeasures in AADL?
So we didn't do the modeling per se in this particular effort when doing that, to model and how it works, but I know there's plenty, with abandoning, of course, and other type of thing, case, and it's the I like the whole compliance aspect, but then the modeling of the impact of the countermeasure per se, where we quantitatively look at the impact of the countermeasure. And having done that, I know when inherently AADL is used to evaluate timing and behavior and all the resource utilization. So you could see that knowing when you're trying to do IPsec, or you're trying to do MACsec, or you're trying to do those type of things, what is that latency? I mean, that seems, it's still something that will be worth doing. Definitely with some of the modeling that exists, it will be a matter of looking at the live data and see what those impacts to CPU memory and latency will be. So that's a great idea, right? To basically do that. I mean, it should be just measuring that live data, but not this effort didn't actually look at that at all.
Hey, thanks very much, Ricky.
Yep, thank you.
Thank you for your presentation.